So I want to just give a perspective of what is DC and what is small signal. When you go to RF, right, of course I'm talking about small signal. For RF power amplifier, it is no longer small signal because you have a large signal, right? But now I'm only talking about small signal. So what does it mean? So on the right, I show you a circuit. It's possible not all of you know this well. This is something called common source amplifier, but I'm going to show you, right, how it works. So you see that this is a transistor, and we have the gate here, we have the drain here, and we have the source here. And we bias it with 1.8 volts of VDD, right? So this is ground, this is VDD to the drain. But we don't bias the transistor directly for a useful circuit. Sometimes you may have other transistor. In this simplified version, it has a resistor RD. Okay, and at the same time, at the gate location, we are going to apply a variable voltage. So what does it mean for this variable voltage? I zoom out to here. It may be that we bias it at a DC value. Maybe this is 1 volt. And that is what we call the bias of the circuit. 1 volt when you don't have signal. And then you are going to add signal to it. You can use capacitive coupling or whatever. But the point is that I'm going to make this signal to change from 1 point, let's say 0.1 volt to 0.99 volt, which means this amplitude is plus minus 10 millivolt. Is this okay? So your signal is like, it cannot exist by itself. You need to put on top of the DC bias in order to make the circuit work, right? So that's why usually when we have this capital letter, capital GS, it means the total value of the signal. So it changes as a function of time. But we can see it as we can see it as, maybe I think usually people use a lower case, that's the total signal, as a DC bias plus AC signal. So this is the 1 volt and this is the plus minus 10 millivolt. That is the total signal that goes into the gate of this transistor. Make sense? Are you okay with this? Now, in this setup, then let me ask you, if VTH, let's say VTH equal to 0.7 volt, is this transistor on or off? On. Why? Because VGS is larger than VTH, right? But VGS is not 1 volt all the time, right? Because after I add the small signal, right? So it is varying, right? But yes, you can say it is 1 volt when I did not apply the signal. So this transistor is on, then there might be a current going down that is 1 milliampere, which is IDS. Do you agree with this? If I turn on the transistor, there should be current going through the transistor, right? Now with this, then what does it mean? It means if I don't have the signal, then I have 1 milliampere of ID flowing. If I have 1 volt here, 1 volt at the gate, then I have 1 milliampere of current going through this transistor. Is that okay? Now what if I make the gate voltage larger? Do you get larger current or smaller current? When I make the gate voltage larger, do you get larger current or smaller current? Larger, right? Just a transistor, right? Because I equals to W on L mu C ox divided by 2 VGS minus VT squared. So if I increase gate, of course the current will increase, right? This is the drain current, right? Then what happened? That is what we are saying now. When the VG increase to 1.01 volt, this might becomes 1.001 ampere. And when VG decrease to 0.99 volt, this might be 0.999 ampere. Milliampere, sorry. Milliampere. So I can also say that the current here is the DC current plus minus 1 microampere. Make sense? Now, what we care about in analog circuit and RF circuit before you go to distortion is this small signal model. We will talk about, say, the gate voltage is plus minus millivolt, 10 millivolt, and the drain current is plus minus 1 microampere. This is the small signal, okay? But we assume that we already correctly bias it at 1 volt and 1 milliampere. Is this okay? And that is the difference between DC and small signal analysis. And this is the procedure if you want to do the thing completely. First, you assume there's no small signal. You do the DC bias analysis, which we are not going to do this in this class. I assume you would do it, right? And I mean, we won't test this. So basically, if I have 1 volt here, you solve the whole circuit, solve the transistor equation together with the KCL, KVL. Then you find that this is 1 milliampere. That is the DC bias. Once you get the DC bias, for each DC bias, you actually have some different AC parameter. What do I call? Small parameter. You then extract the small parameter, small signal parameter. What is the meaning of the small signal parameter? Two of them are very familiar to you, GM and Rout. What is GM? In English, transconductance. Rout, output impedance, right? We will look at this again. There are still other things, right? But based on this, then you have the transistor that becomes simplified. I will show you later. And then you analyze the whole circuit, right? You just analyze the circuit. What do you want to get in this circuit? For example, input impedance, output impedance, bandwidth, etc. Or GM, your capital GM, right? Or the gain of the circuit. So for those who have not learned this before, I hope you agree with me. For every circuit, you need to bias it at a DC. Then you apply small signal to it. And the so-called small signal analysis is just to analyze how this small change of input causes the small change at other places. And by assuming this DC already solved. So you are not going to solve this circuit by solving what happened to when the voltage is 1.01 volt, 1.001 volt, 1.005 volt, all this data, right? All this point. You solve for the DC, you know how it is biased. When a transistor is biased at certain voltage, then it has a certain GM and Rout. And then you do the small signal analysis. Any questions? Now, it's not straightforward, but we will keep repeating, right? So you need to link to this later again. Now, what did we say in lecture 4? This is just slide from there. We talked about the ID-VG curve of transistor, remember? When your VG is smaller than VTH, you have no current. This is linear scale. Then your VGS is larger than that, then you have current, right? That is exactly what I'm asking you. When the VG is 1 volt, this is VTH 0.7, I do have current going through my drain and source, okay? Now, but I can put my VG at different point. For example, my VG can be 1 volt at here. My VG can be 2 volts at here. This curve was not drawn well. It's supposed to be more curvy, not a straight line. Then at each point, you have different slope. Let me ask you again, what is GM? GM is transconductance. It's the change of the output current, which is the drain current, divided by the change of the input voltage, which is the gate voltage. That is exactly what we are seeing here. I increase the gate voltage by 10 millivolt. How much current will the drain voltage change? In this particular case, I increase by 10 millivolt. The current will increase by 1 microampere, right? This is just an example. Here, the same. In principle, if you don't do small signal analysis, you need to solve this complicated equation together with the whole circuit. But now, for example, you say, I bias my gate at 2 volts, and then let's say my drain is at this level, so I need to look at this curve. Now I change my voltage by plus minus 10 milliampere. I try to find out how much current it will change. And it turned out to be plus minus 10 microampere. And this is just the slope. So it turned out to be 10 microampere divided by 10 millivolt, which give me 1 millisiemens. Any questions? Right? So, and you can imagine, let's say I bias my drain voltage at this point. Then the slope will be different. The GM will be different. Right? So this one tells you that when you bias, you DC bias it at different voltage, you have different small signal parameters. Okay? To correlate to here, it basically is saying that if this V out is biased at a different voltage in the DC bias, because you can have a small or a large resistance. When you have a small resistance, you have a higher V out, right? Because less potential drop. Then you have a different GM for this guy, in principle. Okay? So that is GM, right? I remind you. And we also talk about our outs and what type of curve is this? You should be very familiar with this now. Huh? IDVD. Right? So I will pick one VG. Maybe this one is VG at, let's say this is VG equals to 2 volt, for example. Then I sweep the VD. In this region, I try to increase, right? I try to change my VD by plus minus 10 millivolt. I want to see how much current it will change. And by definition, delta VD divided by delta ID, which is 1 k ohm in this case, is the output impedance. And again, do you see that? I bias the VD at different place, I might have different slope. At here, I have this slope, at here, I have this slope. So again, our outs depends on the DC bias. And DC bias are what? Gate voltage and drain voltage, which then translate to drain current also. Okay? So what I want to show you is this, right? Then let's take a look. One more thing. Unless we want to make a resistor, we usually bias the transistor at saturation mode. Do you still remember saturation mode? Saturation mode is when, this is a classical case, I mean, non-channel case, when VGD, right, it is smaller or equal to VTH, which implies VGS minus VSD plus. Yeah, minus VDS smaller than VTH. Okay, so if you have a large VD, of course, then you can go into the saturation mode easier, right? So we care about saturation mode. And because of saturation mode, then it means the current must be W on L mu C off, right? This is something good to memorize. If you, yeah, I think you should memorize this. Okay, that is the GM, right? I mean, that is the current. Then what is the GM? Again, can you tell me what is the definition of GM? Change of drain current. Okay, voltage. Thank you. Right, you need to say it then, so that you can remember. Then you differentiate ID with respect to VG, right? How do you do differentiation? The only variable is VGS, right? So I just need to put this out, W on L. This is a constant, I keep them. And then that is square times 2, and then VGS minus VTH, right? That give me W on L, mu C ox, VGS minus VTH. Again, here clearly show you that if I change my VG, I actually have different GM. So real biasing is very important. So this is the equation shown here. You can try to derive this by plugging the equation into here. They are equivalent. These three definitions of GM. Okay. Now GM is very important because it's related to the gain, right? So as a circuit designer, this is the GM. What can you change in order to change the GM as a circuit designer? See, W, you can change W, you can change L, because you already done the layout, right? So what can you change? What do you do in your layout? You change W, you change L, what else can you change? You think you can change COX? COX is, remember, COX is per unit area, cap per unit area. It's not about the total, it's not about the total capacitance. Yeah, what else can you change? Huh? Do you think you can do change mobility? Well, you can argue actually. You can say, okay, because now they use stress technology, so I deliberately change my layout so the stress will be different. Or hammer it, no, you cannot say that. And that's a good point if you think in that way. Yeah, but let's assume you cannot change. Just like the keyword is, this is a process defined, right? As a circuit designer, you cannot change it unless you are Apple. Right? So you are going to have like 1 million, 10 million wafer a month from TSMC. Maybe they're willing to change for you, right? Otherwise, you just take whatever they give you. Another thing you can do is VG, right? Because you can design a circuit to bias the transistor at different voltage, right? So in your project, these are something you want to change to achieve the goal. Any questions? And of course, when you change VG, you also change ID, right? That is relevant to here, ID. Yeah. Yeah, that should be called just a simplified version. This one? Yeah. Because you want to not to turn, think in this way, you don't want to turn off the drain size, right? You want to have pinch off to have saturation. Pinch off means it doesn't. So VGS smaller than VTH means you cannot turn on the channel on the source side, right? Yeah, it's correct. Think about what I just said. Okay, and go back to check the cheat sheet. And again, what I say is that saturation means you have pinch off. You cannot turn on the drain size channel. Yeah, and in order not to turn on, you need to have smaller than VTH. That's a way that you can memorize. Another way is when you, there are many ways you can verify your fault. For example, here you can also say, I know that if I have larger VD, the chance of getting saturation is easier, right? If VD is small, you go into linear mode, right? Yeah. So you have a large VD, this becomes negative. Isn't that it help me to get into saturation? That's a way of thinking it. Yeah, you can, of course, but they're equivalent, right? You can say VD is greater than. You can swap them in any way you want. They are the same. Okay. I want to talk about the output resistance. At this point, I think I failed to introduce the channel length modulation to you before. I think I did not talk about that. I only talk about the R out, right? Did I talk about channel length modulation in this class? I don't think so, right? So I have been telling you that I equals to, maybe I mentioned a little bit, I forgot. L mu C ox divided by 2 VGS minus VT squared. That is the saturation. That is this point. In this region, it is the saturation. And again, here we repeat what we said earlier, VDS larger or equal to VGS minus VTH. Right? That is saturation. And like what you said, VDS move to there, VGS minus VTH, right? So this is the saturation, which is almost correct, isn't that? The current is almost constant. Does not depend on VDS. But now you probably will argue with me. It does. It increases a little bit when I increase VDS, right? So this is called channel length modulation. I really forgot. I thought did we discuss this actually? I think we discussed this, sorry. But I did not give you the formula, the channel length modulation. It does depends on VDS. So empirical way is to say this current goes up with 1 plus lambda times VDS. This lambda is very small, right? For example, the lambda can be 0.01 per volt. A very small lambda. Which means when you increase VDS, because this is small, your current does not go up much, right? Because you increase 1 volt, lambda this term only becomes 0.01. Then you just increase the current by 1%. 1 plus 0.01, right? It's 1.01, right? Make sense? The reason we want to introduce, because now we want to find the output resistance. Although it's large, I want to find is the value, then of course I need to have a finite value, right? So by definition, again, what is R out? Can someone tell me? Change of, say again? Change of VD versus change of ID. Very good, yeah? Now, this is not easy to do, but we just realized that this is just the reciprocal of this, right? Change of ID for partial ID, partial VD, 1 over it equal to what we want, right? So we do this step by step. So, I mean, no need to step, this is easy. So when differentiate ID, this is just ID, with respect to VDS, everything is constant except the last term, right? So this is W on L, mu C ox, VGS. Again, VGS constant because we're talking about a certain VGS. This is the DC bias I told you earlier. I bias it at 1 volt. Then you have this term. I bias it 2 volt, right? Times what? How do you differentiate this term? 1 plus lambda VDS. What do you get? Just lambda. Yeah, 1 is gone, right? VDS is gone. Now, this one, if you look at this term, this is just like ID, although not exact. But it's a good approximation. Because with different VDS, I only increase the number by 1%, 2%. Right? So then we say, hey, this is just similar to approximately equal to lambda times ID. Because I claim that this term is approximately equal to, or I can say this term equals to ID divided by 1 plus lambda VDS. Right? Lambda plus 1 plus lambda VDS move to here equals to this term, right? And because lambda is small, this is approximately equal to ID. Right? Anyway, this equation is approximation already. Yeah, but of course not that much. So R out is just 1 divided by lambda ID. Now, can you change lambda? Let me ask you, can you change ID? Of course, you bias it differently. So by biasing the ID differently, let's say smaller ID, you actually get larger output impedance. Do you know if you can change lambda? This one you did not learn if you have not learned the circuit before. As a circuit designer, do you think you can change lambda? Circuit design level. No, just for a transistor. I mean, I'm talking about changing lambda, not changing R0. For a single transistor. But then if I say that, you may get confused. But I mean, I ask you to draw a transistor. Will you be able to change the lambda of the transistor? Do you know? Already given, but actually you can, which I did not discuss. Lambda is channel length modulation, right? The parameter for channel length modulation. So again, do you still remember I talked about why we have the channel length modulation? It's because of the pinch off, right? Once you go to saturation, you pinch off at that point. Let's say this is VD equals to 2 volt. And then you further change this to 4 volt, for example. Then maybe you pinch off at this point. Remember this one? Effectively, your channel length is shorter. Effectively. Right? Now, how much shorter? Shorter by delta L. If I have a very short channel already and you short it by delta L, that is a big change to it. But what if my transistor is very long? Let's say 1 kilometer. Even you short it by 1 millimeter, it doesn't feel anything. Right? So this really depends on the relative change delta L over the L. So what you can do is make your larger L, smaller lambda, right? Again, the point is the change of the effective length becomes insignificant when you have a very long channel. And this comes to the reason why all the analog circuit designer really don't care about 2 nanometer, 3 nanometer. I mean, not now it may be okay, but in the past when keep shortening it to 65 nanometer, 45, 28 nanometer, they still want to use 100 nanometer because they need a certain length to have a small enough lambda, so you have a large enough R0. Right? So you usually will see that they are very, very large. And another reason is the so-called mismatch. Although it's not a part of this class, but it's good to learn this. When you design a circuit, very often for analog, for example, something called differential pair, you actually need to put 2 identical transistors next to each other, right? If you use the smallest available channel length, there will be variations. Because this one might be 40 nanometer, this might be 41 nanometer. That is already 2.5% of change. And actually can be more than that, maybe 42 nanometer. And you are not matching, then you will lose all the benefit of differential amplifier, including the noise cancellation or whatever, right? Common mode noise rejection. So you want to make it larger. Maybe let me make it 100 nanometer or 80 nanometer. Then the original 2.5% error now will become 1.25%. Right? Then it will be easier. This is just because of the fabrication process, right? You draw something with 40 nanometer. After printing, it will just have a lot of variation throughout the wafer and even within the chip. You cannot control it. It's as if I ask you to use your bare hand to draw 2 squares. You cannot make them exactly the same. But if I ask you to draw, how about you draw it as large as 1 kilometer by 1 kilometer? Then your error might be very small because you can control it up to 10 cm, for example. But I ask you to draw it 1 cm to 1 cm. Maybe you can only control to 2 millimeter. That is a big ratio of error. Okay, so that is another reason we don't mind to go to a larger device. Okay. Okay, then what is small signal model? That is what I want to further discuss. We understand that we have the DC bias, so you build up the stage. And then on top of it, we apply small signal. And all our goal is this. I want to know if you add a superposition of small signal on top of the DC signal, how would the output change, right? And again, I only care about the small signal, not the total signal. So then someone came up with this circuit. Now the transistor is no longer this device. This device equals to I equal to W on L mu C ox divided by 2 VGS minus VT squared times 1 plus lambda VDS. This is nonlinear. This is large signal, right? The main point, it is nonlinear, which is very troublesome to solve this equation with other part. If I have two transistors like this, you cannot solve it. You need to use numerical, right? Maybe use a spice or whatever. But now, once I know that I have a proper bias, then I can come up with a circuit to represent this one: gate, drain, and source. This is a linear circuit. What does it mean? It will say what is the small signal VGS. So here is this model. For example, I'm doing this. This is 2 volt. And then I vary this by plus minus 10 millivolt. This one is 2 volt when you're doing the whole thing. Okay, and this is plus minus 10 millivolt. Now you don't have this 2 volt in your equation. It's gone. Then what is the effect of the 2 volt? It is embedded in the parameter GM, because GM depends on your bias. Okay? So this is VGS and this is ID. So let me just remind you again, what is the meaning of increasing VGS? It is like this. In the DC or a total signal, maybe I change it by 2 volt to 2.01 volt to 2 volt to 1.99 volt. This is what you really get when you measure your circuit if you have a voltmeter. But in the AC domain, which is here, it's saying I start with 0 volt. It becomes 10 millivolt. It goes back to 0 volt and goes to negative 10 millivolt. Is that okay? Now that is the main point, because if you don't, some students, right, they did not understand it well, or including when I was studying this topic, I will feel weird. Why you can have negative gate voltage and there is still current conducting? This is not the negative gate voltage of the gate. It is just a small signal. When you add this negative 10 millivolt to this 2 volt, you actually have 1.99 volt on your transistor gate. So it is on. Okay? So is this model correct, right? I claim that this can model the transconductance. Then let's see, right? So from the picture, from this picture, it tells us something. If you are not familiar with this, it says that ID equals to GM VGS. That is what you say in this picture. This is something called voltage control current source. The amount of current going here depends on the voltage across VGS. And he's saying that it's GM times VGS, and due to KCL, Kirchhoff's current law, whatever comes here need to go through here, right? So the ID equals to GM VGS. This is what you say in this picture. ID equals GM VGS. And then, which means GM equals to ID divided by VGS. But remember, this is small signal, which means this is delta ID, delta VGS, right? And this is just our definition earlier of GM. Make sense? So So to be frank, right, if you feel confusing, I don't need to really understand what I'm trying to do here. But the point here I'm trying to show you is that this circuit indeed capture the GM, the transconductance aspect of a transistor. And I show you by saying that the current indeed is given by GM VGS, and based on this, GM equal to partial ID partial VGS, which is the same as our definition. So from now on, when you do small signal, you will replace the whole transistor by this circuit. And this is linear. There's no quadratic term. And because it's linear, you can do superposition. If you have a very complicated circuit, you just solve the excitation one by one and then add the result together. Okay, any questions? Now, if no, then it doesn't matter to repeat a little bit more. How about the output impedance? Here, we did not capture the output impedance, right? So, again, what is the meaning of this circuit? I think now you understand what I'm talking about is the small signal. So, here we have VDS. What is the meaning of increasing VDS? Again, when I have a DC or a total signal, right? Biasing plus the small signal, I might go from, for example, let's say still 2 volt to 2.01 volt to 2 volt, going up and going down, right? Remember, it's just signal, becomes 1.99 volt. And what we care about again is the AC signal, means I have 0 volt drain output, becomes 10 millivolt, becomes 0 volt, becomes negative 10 millivolt. And again, here, some of you may say, how come you only have 10 millivolt and it's still in saturation? 10 millivolt should be in linear mode, right? But just because this is AC, the total voltage is 2.01, not 10 millivolt. And it is 1.99 at a certain point of time, not negative 10 millivolt. Okay? So with this, we dump everything to the background. Then again, then what is the effect of this 2 volt? How come you don't need to put in the DC? Because we add a resistor here, which is dependent on the DC. Remember that? R0 equals to 1 over lambda ID. ID depends on the VD and VG, and that's why it controls R0. Okay. Again, is this model correct? Then let's try to study what is the meaning of output impedance by definition. Say again, do you remember what's the meaning of output impedance that we just learned? Partial VD, partial ID, right? Which is equal to the small signal VD divided by the small signal ID, right? Correct? This is just the slope, right? It's just like what we're doing here. This is VD, maybe 2 volt, and then I do it plus minus 10 millivolt. And then same for the ID. So that is good. That's the definition. How about in this circuit? By definition, which you have not learned, I will say again later, is that the output impedance is equal to the V out divided by I out. Okay, so this is ID, but this is also the output current. This is VDS, but this is also the output voltage. But you need to ground the input to 0. This is definition, okay? So don't ask why. Let's just use this one. We don't have time to go too deep. When you measure the output impedance of circuit, you need to short the input, which also makes sense, right? Because you don't want the input signal to interfere the characteristic of the transistor. Remember, Rout is a characteristic of transistor. You want to make it independent of the input signal. Just like how heavy I am, you should measure as I'm not eating today, right? Because I can eat a lot today or eat very few today. Then my weight, which is my characteristic, becomes meaningless. It can fluctuate plus minus 1 kg, for example, right? So you will say, okay, I'm going to measure your weight. From now on, don't go to toilet and don't eat. That is your weight, right? And that is like the input need to be 0. So when input equals 0, but what is the input? Input is this one, V in equals to VGS. So this is equal, and V out is what? ID divided by VD. And then V out, V in is like VGS equals to 0. When VGS equals to 0, right? When VGS equal to 0, that implies GM VGS equal to 0. Basically, I don't have this component when I grant this one. When VGS equal to 0, I don't have current, so the whole thing is gone, right? So now if you try to find what is ID divided by VD divided, so I say something wrong here. No one correct me. Yeah. This one should be ID divided by VD. VD divided by ID. Look at this circuit. I don't have this component. What is the VD divided by ID? Yeah, but just R0. I only see one resistor, right? VD divided by ID is the resistance value. That is the definition of a resistor, right? So definitely this is what I'm talking about here. Yeah, this equal to, so maybe I think at this one I may confuse. I should not say R0. Let me just call it R out. Okay, and so this equal to R0, right? And then if you combine this, they are consistent. Right, so I give you something consistent. If it's confusing, okay, no need to really able to prove this. But the main point is now, if I give you a transistor, you can change it to this circuit, which is a linear. Yeah. R0 is what? This is a model of the small signal. The transistor is here. What you draw on the layout or the gate oxide, whatever, this is the transistor. Then we bias it. Then the rest for the small signal, I can model as this, how it works. So remember, R0 is not a physical transistor. Okay? And GM, this voltage control current source, is not really a voltage control current source. You cannot make a voltage, it needs to be a very complicated circuit to have a perfect voltage control current source. Right? Again, this is just a model to model the transistor. Yeah. It's just that it works. For example, if R0, he's asking why R0 is in parallel. If you put R0 in series, right? Then when here I don't have current, this is open circuit. Then your output impedance would not match this equation. Makes sense? If you put R0 in series with GM-VGS, now if I try to find the output impedance, I will look into here, right? And then now this is open circuit. I see infinite impedance because the current cannot go through. Then you cannot capture the model that you have. I just happen that this works well. Yeah. Yes. So thank you. Let me just say it in particular. Say here, if someone say, okay, there should be RO, when we do not draw it, it means it's infinite. Yeah. Which one? This one or the next one? Here? I'm talking about VGS. Yeah. This is VDS. Yeah. Okay, so if you don't understand everything, fine, but you need to play the game. The game is now you accept this is the small signal model. You plug in, I give you a complicated transistor circuit, replace all the transistor by this circuit, and then you solve it only with KCL, KVL. No more diode, no more transistor equation. Okay? How about PMOS? Here, the only thing I want to mention is as a practice and also make it clear, right, how to draw it. It turns out it's the same. If you can memorize the model for NMOS, you can memorize the model for PMOS, because here is the model from NMOS. I just flip it upside down. And you find that it's exactly the same as PMOS. Okay? So this is the source, this is the drain, and this is the gate. But it will be good, right, to study a little bit more. What is the meaning of this in the real circuit? What's the meaning of Vy? Of course, it's the Vg, right? But what does it mean? So let's look at the structure of a PMOS. I mean, the circuit of PMOS. This connected to VDD, 5 volt, for example. And this is the source, okay? For PMOS, I don't go to those, but those 134 I told you, always ask you to memorize. For PMOS, the higher potential terminal is the source. For NMOS, the lower potential is the drain, is the source, okay? So what can it be? Maybe I start this at 5 volts. Not 5 volts, sorry. Maybe this is, let's say, 5 volts. This is 4 volts. Okay, the gate is at 4 volts. And then you have a current. Let me don't draw here. Let me make this, right, make it clear. I have an ID equal to 1 milliampere. Okay, let's don't think about small signal or whatever. My question to you is that I have 4 volts at the gate. If I change it to 4.1 volts, what happened to my current? Is it larger or smaller? And smaller, very good. But the easiest way to think about that is, why don't you just keep larger, make it even larger? Let's say 4.9 volt or even 5 volts. Do you have current? No, right? Because now you turn it off. This is PMOS. You want the gate to be lower than the source by the absolute value of the threshold voltage, right? You think in this way, right? So if the difference is large, I know that I have more current. So if I increase the gate voltage from 4 volt to 4.1 volt, I will expect this one will become 0.99 ampere. Make sense? But I want to see it from a small model perspective. 0.19 ampere is just equals to I have 1 milliampere going down, because this is the DC bias. Before I apply any small signal, it has 1 milliampere going down, right? Plus, I have 0.01 milliampere going up. 0.99 going down is the same as 1 milliampere going up and 0.01 going up. Right, sorry, 1 milliampere going down and 0.01 going up. Make sense? Because you just addition, right? For example, you say, okay, the river is flowing with this rate, 10 gallons of water from left to right. You can argue, say, oh, no, it's 11 gallons of water molecule from left to right, but then 1 gallon from right to left. No one can. Physical effect is the same, right? I mean, mathematical effect is the same, I should say, modeling, right? And what is this? This is the DC bias, and this is the small signal. And this is exactly what it is talking about here. When I increase Vy, then the difference, remember this is grounded, because this, maybe some of you will get confused also. maybe it's good to talk about now. Isn't that I say it is VDD, why I grant it, do you know? It's AC grant. Because this is a small signal. Small signal is talking about what? How much disturbance to the DC. For a VDD equal to 5 volt, it means I have 0 small signal because I always keep it at 5 volts. This is a perfect voltage source, right? So you don't see any signal. That's why this is grounded. When I increase this from 4 to 4.1 volt, then it means Vy will change to 4 volt to 4.1 volt, means that Vy equal to 0.1 volt. That is what it means. So this one increase, okay? So you will figure if this one increase, then it means just that I have more small signal current going out. And that's why I have smaller overall current going down. Is this okay? I will encourage you to go back to think about what I've talked about, right? I really think that this is something very confusing for electrical engineer, for many of us, right? Even when I was a student. If you can understand that, it's great. Not going to test in the exam, but this type of understanding can help you in the interview and understand the small signal circuit, right? Other than that, all you need is you accept what I said. This is the small signal for PMOS. You see the PMOS, I asked you to do small signal analysis, plug this in. Don't argue. Unless you understand this, you have more questions. If you don't want to understand this, then don't argue. Just use this one. And it's possible in the future, some people give you something more complicated, and that is how it works. Then you just put in that model. You trust them. Make sense? Now, so that is the summary. Maybe no need to waste time to talk more, but here I told you that how you get GM, how you get R out. So this complicated nonlinear transistor become a linear subcircuit. A few things I want to mention also is how do you measure the input impedance of a circuit? This one can be 1 transistor, or it can be 1 trillion transistor. I want to find what is the input impedance. Now you go back, right? When we say about input impedance, it's just like you have a resistor. You are asking what is the resistance value. And how do you find the resistance value? Experimentally. Yeah, you apply a voltage across it, then you measure the current, right? That is what you do since the elementary class. Just put the 1 volt across the resistor. I get 1 milliampere. Okay, so this is a 1,000 ohm resistor. That is exactly what you do. You apply a Vx and then measure the Ix. So R in equals to Vx divided by Ix. But it is not a resistor. It's a complicated circuit. It can have many terminals. If for those terminal, the output terminal, you try to do something, for example, I want to short it, or I have a loading here, you will get different current. You can imagine that, right? Another example, maybe not a good example. How to say that? It's just like you measure my weight. You want to make sure that I'm not carrying a backpack, right? Something like that. So our common consensus is what? You need to make sure your output I out equal to 0. Means you have an open circuit. This is I out. We do it in another direction usually by definition. This is I out. Okay? It means you have infinite loading. This is related to something, but we won't discuss here. Because we expect ideal loading, but I think we don't have time to go to there. Just trust me, right? Then how about you measure the output impedance? You do the same thing, right? R out equals to Vx divided by Ix, like what it is doing here. Okay, you have a very complicated circuit, right? But again, as we said earlier, I already told you, we want to make sure the V in equal to 0. So we short it because this is V in. This is V in, right? Again, because when you have a complicated circuit, you try to do something in the V in, then it's just easy to understand because this can be an amplifier. You do some to V in, and then you actually can change the Ix a lot. You can provide Ix to me instead of taking Ix. Then I have a negative output impedance, right? So that is how you define it. So this one goes back to what I said earlier here. When we try to measure out of this transistor, we will ground the V in, and because we ground V in, this one is gone. Not because we want to take this away, but just by definition, we need to ground it. And we ground it, then this one is gone. So this is the definition. Any questions? Okay. Actually, last time when I taught this, I did not review this, but maybe it's good that I do it this time, right? So when you do a DC and small signal analysis, that is what I said. You see, this one is a rather complicated circuit. This is something called common source amplifier. Your input signal is here, and then you change the drain current. As a result, you change the output voltage because the voltage across this resistor is changing. And then you come to here. This is another common source amplifier, which we will learn later. But what type of transistor is this? PMOS. And that's why it's common source, because the source is here. If you try to solve it, it's very difficult to solve. But you can first find out the DC bias and then build the small signal model to solve the gain. Okay? So what do you need to do when you try to create a small signal model? The first thing, any constant voltage, you need to short it. Any constant current, you need to open it. Well, I already mentioned that. Anyone want to try to explain one more time? Why for a constant voltage point, I want to short it? Yeah. Yes, because it's constant voltage, then of course across that 2 point, you have a constant voltage. So there's no AC, right? Because there's no change. 5 volts is always 5 volts. You do not get plus minus 1 millivolt or even plus minus 1 nanovolt, right? So in the small signal, it is short. So using the same token, can others explain to me why if I have this is a current source, with a constant current, why I will open it? What does it mean? When you have constant current. Think about DC and AC again. We're talking about current, not voltage, right? Constant current means what? Do you have variation in current? No. Then it means there should be no AC current, right? Then what is the condition for no current? Open. Yeah, infinite impedance. Open. Right? So if this is constant, I open it because there's no AC current. Right? So based on this, you see clearly from here to here, VDD, it becomes this too. Grounded. Okay? They're grounded. How about this one? Open. I don't need to worry about this. It's open because it's a constant current. Okay? Whether it works or not, that is another thing, right? And then what do I do? This is gate, this is drain, this is source. I put this as gate, source, drain. This is for MOS. This is the model I gave you earlier. Where is R0? Actually,
well, so I think for the first state,
this is RD1, you're right. Yeah, there's one thing he said, usually RD1 dominates, but what it means here is that I also assume no channel length modulation. So R0 equals to infinity. I do have R0, but it's infinity. So don't need to draw it. Okay. Then I do this. Gate, source, drain for the PMOS. So I get gate, source, and drain. I just connect them. You see that I connect RD1, VDD become ground, RD1 to drain, drain to gate, source to VDD again is ground, drain to the output. Do you see that? If you have not done that before, it's a little bit, you need to do some practice. But I have video, you can, I already sent you at the beginning of the this semester, right? E124 video. There are many examples. So if you have not taken that class before, please take a look to practice. Okay? Okay, so good. We are good with this. So any more questions? So we will keep seeing this. Later, I will ask you to refer back to this when we are doing some more, when we are doing those small